Hello friends, welcome to another chemistry video from eLearn. My name is T-Man and I'm a chemistry tutor at eLearn. In this video, we will discuss chemical equilibrium, which in essence is about how far a reaction goes. That is, what proportion of reactants are converted to products. Think popcorn. At times, not all kernels pop. Without much further ado, let's delve into it. We will start by defining a reversible reaction. A reversible reaction is any chemical reaction that progresses in either or both directions. This means that reactants can be converted into products, and the products themselves can be converted back to reactants. Now, for this type of reactions, we should use the reversible sign. There are a few well-known examples. The first one is the thermal decomposition of calcium carbonate. We know that calcium carbonate decomposes to form calcium oxide and carbon dioxide. And it is also well known that under the correct conditions, calcium oxide reacts with carbon dioxide to form calcium carbonate. The second reaction is the Haber process or Haber process to convert nitrogen and hydrogen into ammonia. And it is also well known that ammonia decomposes to form nitrogen and hydrogen. Third common chemical reaction is the oxidation of sulfur dioxide to form sulfur trioxide. And the sulfur trioxide also decomposes to form sulfur dioxide and oxygen. So these are a few reactions that are known as reversible reactions. There are a lot of reactions that are like this. Well, this doesn't apply to all chemical reactions. There are some that cannot be referred to as reversible reactions. Now let's go on to dynamic equilibrium. Now, dynamic equilibrium can be defined as a balance in a chemical reaction in a closed system in which the rate of the forward reaction is equal to the rate of the reverse reaction, and the concentration of the reactants and products do not change. Now, what is important when we are defining dynamic equilibrium is the term balance, which means we have balance between the two systems, and this can only happen when the reaction is reversible and also we have a closed system. Now, what do we mean when we say a closed system? We're simply saying that none of the reactants or products are allowed to escape. Now, this applies mainly when we have gaseous substances in the reaction. If they are allowed to escape, like for instance, the thermal decomposition of calcium carbonate to form calcium oxide and carbon dioxide. If the carbon dioxide is allowed to escape, we do not have products that can recombine to give you the reactants. So whenever we have dynamic equilibrium, we need to have a closed system. And whenever you are asked to define dynamic equilibrium, you have to specify that the system is a closed system. Another thing is that the concentrations of the reactants and products do not change. This does not mean they are equal. They simply do not change. Let's say, for example, you have 2 moles per cubic decimeters of a substance X at equilibrium. That concentration will not change. But what you need to understand is that the reaction is going to continue and the microscopic properties continue to change, but the macroscopic properties do not change. Like, let's look at an example, the reaction between hydrogen and iodine to form hydrogen iodide. Now, when you look at this reaction, it's a reversible reaction. And the good thing with this reaction is that we have a substance that is colored. Iodine, vapor, is colored and it's a purple color. Hydrogen and hydrogen iodide are colorless. So what happens in this reaction is when we start the reaction, we mix hydrogen and iodine, we are going to observe an intense purple color for the iodine. But as the reaction progresses, the purple color is going to continuously fade as the iodine and hydrogen are being consumed in this reaction. But we will get to the point of equilibrium where the color of the iodine stops changing. And when we get to this point, we have dynamic equilibrium. The color remains constant, which means the amount of the iodine stops decreasing. But this doesn't mean the reaction is stopped. The reaction actually continues. We have iodine that is reacting with hydrogen to form hydrogen iodide. At the same time, hydrogen iodide is breaking down to form hydrogen and iodine. So the issue that we have here is that the rate of formation of hydrogen iodide is exactly equal to the rate of decomposition of the hydrogen iodide. Therefore, the amounts are going to be the same. Now, let's look at the factors that affect a system at equilibrium. We have three factors that can be used to alter the position of equilibrium, that is, to affect equilibrium position. We have temperature, concentration, and pressure. So when you are discussing factors affecting equilibrium, you need to know that there are three things that you can do to change the position of equilibrium, which is temperature, concentration, and pressure. Just those three at this level. And we use what is called Le Chatelier's principle to explain how these factors influence the position of equilibrium. And when we discuss these factors, there is another factor, the catalyst. The catalyst does not change the position of equilibrium. All it does is it speeds up the rate of reaction, but it speeds up the forward reaction and the backward reaction by the same magnitude. Let's talk briefly about Le Chatelier's principle. Le Chatelier's principle states that if a system at dynamic equilibrium is subjected to small changes in some factors, processes occur that tend to counter the change imposed. So we move on. The first factor that we want to look at is concentration. When the concentration at equilibrium of any species, that is a reactant or a product, is changed, one of the reactions, either the forward or the backward reaction, is favored to counter the change imposed. And this means that the equilibrium position is going to shift. Consider the reaction. Now, when we look at this reaction, if we look at the concentration of substance A, or we look at the concentration of substance B, and the concentration of either is lowered, this means that the reverse reaction is favored to try to replace the amount of A or the amount of B that has been removed by converting some of the C and D into A or B. This means that the equilibrium position is going to shift to the left. If we do the same, we look at the same substances, A or B, and then we raise the concentration of these two substances, the forward reaction is going to be favored, and the A or B are going to be removed and converted to C and D, and therefore the equilibrium position is going to change and shift to the right. We continue with the same reaction, A reacting with B to form C and D. If we look at the concentration of the products, either C or D, and the concentration of these substances are lowered, the forward reaction is going to be favored to try to replace the C or D that has been removed by changing A and B into C or D, and this means that the equilibrium position will shift to the right. Same applies to the situation where C or D is raised. The equilibrium is, the reverse reaction rather, is going to be favored, and the equilibrium position shift to the left. So when we are looking at concentration, if any of the reactants of products are changed, the reaction will try to reverse or to counter the change imposed. Now, you need to understand that these are very small changes, and the reaction will try to replace what has been removed or to remove what has been added. Now, the obvious question that you're going to ask me is, how is the amount of A or the amount of B removed? This can simply be done by adding a different substance that reacts with A. If we want to remove A, we find a substance that reacts with A but does not affect any of B, C, or D. That is going to lower the concentration of A, and the reverse reaction is favored. Now, let's look at the second factor, which is temperature. Now, an increase in temperature favors the endothermic reaction, while a decrease in temperature favors the exothermic reaction. You know that an endothermic reaction takes in heat. So what it does is the temperature of the surroundings are going to decrease. And you also know that an exothermic reaction gives out heat, and the temperature of the surroundings is going to increase. So when we increase the temperature, we are going to favor the reaction that takes away that added heat. And when we decrease the temperature, we are going to favor a reaction that replaces that heat. Okay, so let's look at a few examples. We are going to look at an exothermic reaction. And for this one, I've taken the Haber process or Haber process. And this reaction is an exothermic reaction because delta H is less than 0. As you can see in this reaction, delta H is negative 92.4 kilojoules per mole. So whenever you see the delta H as a negative number, that means your reaction is exothermic, and this means that heat is given out. So when the temperature is lowered, in this case, the forward reaction is favored. Remember, the forward reaction is the one that is exothermic, is the one that gives out heat. And therefore, you lower the temperature, the reaction tries to replace that heat, and in this case, our equilibrium position shifts to the right. Now, a point that I'll say now is that if the forward reaction is exothermic, it means that the reverse reaction is endothermic. So when the temperature is raised, the endothermic reaction, which in this case is the reverse reaction, is going to be favored, and the equilibrium position will shift to the left. Let's look at another example, reaction that is endothermic. Well, this simply means the forward reaction is endothermic and the reverse reaction is exothermic. We're looking at the decomposition of hydrogen peroxide to water and oxygen. Positive 98.0 kilojoules per mole. The positive is telling us that the forward reaction is endothermic. So in this case, when the temperature is lowered, we are going to favor the reverse reaction, which is putting back the heat, the exothermic one, and the equilibrium position shift to the left. When the temperature is raised, the reverse happens. The forward endothermic reaction is going to be favored, and the equilibrium position shifts to the right. So that is the factor number 2. The third factor is pressure. An increase in pressure favors the side with fewer gaseous molecules, while a decrease favors the side with more gaseous molecules. Now, what you need to understand at this point is that changes in pressure only affect reactions where there is at least one substance which is in gaseous phase. So let's look at this reaction. The Haber process, nitrogen reacts with hydrogen to form ammonia. Whenever it's a question about pressure, the first thing that you check are the state symbols. We check the state symbols. In this case, all of them are gaseous. Now, the next thing that we do is we check the coefficients in the reactants. For nitrogen, the coefficient, because there's nothing, coefficient is 1. And for hydrogen, the coefficient is 3. We add the two of them, and then we get 4. On the right-hand side, the coefficient is 2. There's only one substance, which means on the right-hand side, we only have one substance. So we only have 2 molecules, or moles if you want. So in this case, we have 4 molecules of gas on the left-hand side, and we have 2 molecules of gas on the right-hand side. So when the pressure is raised, the reaction is going to try to counter that increase in pressure. And you understand that pressure of a gas is caused by collisions between the molecules of the gas and the walls of the container. So if this wants to try to reverse the change imposed, we are going to promote the forward reaction to form fewer moles of gas, or to form fewer molecules of gas, and the equilibrium will shift to the right. Okay, and then we're looking at the same reaction. And in this case, the pressure is lowered. What happens in this scenario is that we still have our 2 molecules of gas on the right-hand side and the 4 molecules of gas on the left-hand side. Pressure has been lowered. The system tries to increase the pressure, and the reverse reaction is favored. Now, this is obvious. We want to have more molecules so that we have more collisions with the walls of the container. And this means that the equilibrium position will shift to the left. Let's look at another reaction. Decomposition of calcium carbonate. And like I've said before, the first thing that we want to do here is to check the state symbols. We have calcium carbonate solid, calcium oxide solid, and carbon dioxide solid gas. This means that calcium carbonate and calcium oxide have no effect because they are in the solid phase. So we do not even check the moles of the solid. We just go and check the moles of the gas, which is carbon dioxide. In this case, we only have 1 because there's no number there. It means 1. Therefore, we have more moles of gas on the right-hand side, which is 1, and less moles on the left-hand side, which is 0. So what happens when the pressure is lowered? The reverse reaction, the forward reaction is going to be favored, and equilibrium shifts to the right. What happens here is the system tries to replace the pressure that has been removed by increasing the number of moles of gas. So when pressure is lowered, forward reaction is favored, and our equilibrium position shifts to the right. Same applies when the pressure is raised. The reverse reaction is going to be favored, and the equilibrium position shifts to the left. Now, when we're looking at pressure, there is a situation where you are going to have substances that are not in the gaseous phase, like a chemical reaction where no gas is involved at all. This simply means pressure has no effect on that reaction. So we need to have at least one gaseous substance in the reaction, either on the reactant side or on the product side. No gas, pressure has no effect. That's the first situation. The second scenario where pressure has no effect is when the number of moles of gas on the left and on the right are equal. If the number of moles of gas on the left and the right-hand side are equal, changes in pressure will not have any effect on the reaction. Okay, so let's move on to the next part. The last factor that we want to look at is the catalyst. Now, we define a catalyst as a substance that speeds up a reaction without being consumed by the reaction. Now, the catalyst alters the rate of both the reverse and the forward reactions by the same magnitude. And this simply means that a catalyst has no effect on equilibrium position, but it allows equilibrium to be attained much quicker or much faster. So when we start the reaction, we mix the reactants together, and then there are no products at all. The presence of a catalyst is going to speed up that reaction to form the products. But once equilibrium is attained, then placing a catalyst will not affect the equilibrium position. All it does is it's going to speed up the forward reaction, and it is going to speed up the reverse reaction, and it does this by the same magnitude. So the equilibrium position will remain unchanged. Thank you so much for watching. Where do we go from here?